Okay, so section 5.2, we're going to be going on to more linear models, right? So more applications, and as opposed to initial value problems, which is what we dealt with in the last section 5.1, we're going to be talking about boundary value problems, right? So boundary value problems typically involve sort of, instead of initial conditions, we call them boundary conditions, right? And so it's basically what happens on the boundary, right? Now, for our purposes, we're going to be dealing mostly with one-dimensional problems, right? So suppose we have a long rod or stick. Let me try that again. Make it sort of a rectangular, right? So this could be, made of wood or metal or something, right? So this is just a beam. You know what a beam is, right? And so it's some length. You can call it L for length. So that's the beam. And if you don't have any weight on it, then we presume it's just a flat beam. I know it doesn't look flat, right? But it's just a horizontal beam. And if you do put a weight on it, like in this picture down here, if you notice, if you put a little weight right in the middle of it, the beam is going to deflect, right? It's going to bend a little bit downward, right? So we can say it bends or deflects. So we have a deflection here. So this is the deflection of what would ordinarily be a flat beam, right? So if this is, oh, that's pretty good. If this is a flat beam, then we're going to add weight to it. Or perhaps we don't have to add any weight. If we just support it at the ends like this, under its own weight, the beam might deflect slightly like that. I could do a little better job than that, right? So the beam might look like this. Maybe that's an exaggeration, but you get the idea, right? All right. So for these problems here, we're going to be thinking about the non-deflected beam as just being the x-axis. In other words, y equals 0. So when you do add weight, or perhaps under the weight of itself, the beam deflects and you get this curve. So we're going to say that this curve is just y of x, right? So this is x. Obviously, in this case, you might think y would be negative because it's downward, but we're going to make the same convention that downward is actually positive. So if you were to graph this, right, like this, oops, it would look the opposite. It would look like this. Maybe I should do that in green. Well, no, it's the graph, right? It's right. So the graph would look like this, but that corresponds to a beam that's deflected downward because of gravity. Okay, right. So just some terminology here, right? We define the bending moment, m, right? So m is a function of x, is called the bending moment. And it's related to the load, which is the weight, we'll call the weight w, per unit length, by this equation here. So it's a differential equation. The second derivative of m is just the weight, right? All right. So you can also define the moment to be this quantity here. Let's see if I can highlight this equation here. So this equation here, the bending moment is this constant E times another constant I times kappa. So that tiny little k here is the Greek letter kappa. And kappa is the curvature of the beam, right? So when it's deflected, it has a curvature. If it's a straight beam, the curvature would be 0. Okay? All right. E is just a constant. It's called Young's modulus. Again, that's something you'll hear in your engineering courses. Perhaps if you take strength of materials, this is going to be an important concept there. For our purposes, it's just a constant. The significance is going to be lost on us for the most part. And I is the moment of inertia. If you've taken Calc 3, you remember the moment of inertia. Again, for our purposes here, it's just a constant. Okay? And if you multiply E times I, you get another constant called the flexural rigidity. Flexural rigidity? Right, close enough. So from Calc 3, you may or may not remember that this is the formula for curvature. But if you don't, that's fine. That's just take that as a definition. So it has to do with the second derivative of y as well as the first derivative, right? And the idea is the first derivative is going to be very small. So even though the curvature might be big, if you notice the slope of the curve here, whether you take positive or negative doesn't matter, the slope is very small, right? The slope is not very big. I mean, obviously, it can't be very big, right? You're never going to get a beam that deflects like this. It's going to break long before it gets to that point, right? We're talking about solid beams here, right? So yes, beams don't deflect that much in practice. So it's reasonable to assume that the slope of the beam is very close to 0. So we're going to make this approximation that the derivative of y is going to be 0, right? Now the second derivative, you know, typically could be a little bit bigger than that, so that's not going to be affected by the first derivative. So if we make that approximation, then the curvature can be approximated really as just the second derivative of y. All right. And in that case, you get a much simpler equation for the bending moment. It's just e times I times the second derivative of y. So if you plug that back into the first equation here, you get a fourth order differential equation, right? Because this is m, right, which involves the second derivative of y, and this is the second derivative of that. So the second derivative of the second derivative gives you the fourth derivative here of y, right? Right. And so this is the equation that we effectively want to solve, right? The solution we want to get is a rough approximation of what the curve looks like, what the shape of the beam will be given a specified amount of weight, right? And that weight might be different in different places. You might place a heavier weight over here and a lighter weight over here and maybe a very light weight here, right? So different weights, the weight will vary over the length of the beam, if that helps. Okay, so yeah, this is the equation we want to solve. Effectively, we want to solve this for y of x, right? To get the shape of the beam. Right. Now, of course, it's going to depend on how the beam is supported, right? So let's start with the sort of the simplest version of that. If the beam is embedded at both ends, so it's basically stuck between two walls like this, right? So we say that it's an embedded or clamped beam at these ends, at x equals 0 on the left and x equals L on the right. Remember, L is the length of the beam. Okay, so this gives us what are called boundary conditions, right? So notice what happens at the left side here, right around here. We can see that the beam, well, first of all, we're just going to say that that's the x-axis. So in other words, y will be 0 here. But it's also flat, right? So the slope is also 0. So when you have an embedded or clamped beam at the ends, both y and y prime will be 0 there, right? So in fact, there's actually 4 initial conditions here. I don't know if I can write them all down for this first part here, for the embedded boundary conditions. You get y of 0 is 0, and you get y of L is 0. So it's 0 at both the right end and the left end over here too. Okay. Right. And so it's also flat at both ends, which means the first derivative is going to be 0 at both ends, right? So effectively, that's a prime, right? Effectively, you have these 4 boundary conditions for this figure here in part A. Okay. Right. Another type of boundary condition you can get is in B, which is sometimes called a cantilever, right? You clamp it at one end. In this case, we're going to clamp it on the left end here. So imagine the beam is sort of fixed here. So it's clamped at this end. And then there's no other end. We just let it sort of, we just kind of let the beam fall a little, not fall. Yeah, we just let the beam loose on the other end. So it's going to have a deflection just due to gravity pulling it down, right? Okay, so it's free on the right end and clamped on the left end, right? So what happens at the free end here? At the free end, well, certainly the slope doesn't have to be 0, right? And remember, it's clamped on the left end. We're calling that 0, so this is going to have some positive deflection, so y doesn't have to be 0. What has to be 0 at this point, and this, again, this may not be exactly clear, what has to be true at the free end is the curvature has to be 0. So the second derivative has to be 0. Now again, that may or may not be clear at this point, but that's effectively what happens. Well, maybe I can explain it this way, right? You get curvature when you push on something, right? When you have a force. Since there's effectively no force at this end other than gravity, right? We're not clamping it, we're not supporting it, we're not pushing or pulling it at any point here. We're just letting gravity pull on it. But other than that, since there's no force, it's just not going to have a curvature at that particular point, right? Okay. The other condition is that the third derivative is going to be 0. And again, that might even be less clear. So the third derivative, obviously, sometimes I put the 3 in parentheses, either way. Oh, that's at L. I'm sorry, not at 0. Yes, because we're on the free end now. The free end, oh boy. The free end is at L. So this is going to be 0. Likewise, this should be L here, not 0. So the second derivative is 0 and the third derivative is 0 at L. What happens at x equals 0? The same thing that happened at the embedded part here, right? So, okay, so that's what happens at a free end. Yeah, so why is the third derivative 0? Because the shear force is 0. The shear force is just the derivative of the bending moment. And that turns out to be 0 at the free end. Again, so in your strength of materials courses, this might be explained a little more clearly. Again, I'm a mathematician, not an engineer, so just take this as a given. There's one other type of support we have, and that's the simply supported, right, or sometimes called hinged. So these are hinged or simply supported. So it's basically just laying a beam down at two points over here at the left and right. Okay, so those are where they're supported at both 0 and L. Okay, so for hinged boundary conditions or simply supported boundary conditions, again, we're going to assume that over here on both ends we get 0. So y is 0 here, y is 0 here. We're assuming that these are at the same height. So the undeflected beam would just be horizontal here. And this would be y equals 0. Right? So that explains the y equals 0 part. Now the slope is not 0 because at the end here, right, it is sort of bending downward slightly. So y prime doesn't have to be 0. What has to be 0, again, is the curvature. In other words, the second derivative has to be 0. So for part C, for hinged boundary conditions, right, say at 0, y would be 0 and the second derivative would be 0. And that's also true at the right end. So we can say the same thing, y of L would be 0 and y double prime of L would be 0. That's not a prime, this is parentheses here. So y at L is 0 and y double prime at L is 0. Okay, so those gives us 3 different types of boundary conditions, the boundary being the two ends at x equals 0 and x equals L. Okay, so we're going to do an example, and this is I hope this is a pretty easy one. This is just exercise 2 from section 5.2. We want to solve the following equation. E times I, again, E and I are constants, times the fourth derivative of y is equal to w of x. And if you remember, that was the original equation that we wanted to solve, going back up here. this is the form of the equation, right? Okay, so, right. So in this case, we want the beam simply supported at both ends. So hinged support at both ends, hinged boundary conditions at both 0 and L. And then the weight is just going to be a constant, right? It's just going to be this W0. And so, right, so the picture here is this, although I messed it up, but, oh, maybe I can try that again here. So it's going to be a little sloppy here, but let me try to draw. These are the supports, and then the beam will look like this. Okay, and this the weight W of x is just a constant, and you can think of that as simply the weight of the beam. If it's a uniform beam, it's just the same weight at each point. So in other words, this is going to be a situation where you just have a beam and you're not putting any additional weight on it. You're letting the weight of the beam itself be what causes the deflection. Okay, and so the beam will deflect, again, very slightly, depending on the strength of the beam, will deflect simply under its own weight. Okay, so this is a good model for that. Just make W of x constant. Don't put different weights at different places, right? So if it's a uniform beam, same density at each point, this is a good model for that. Okay, so so with that in mind, this EI is of course just a constant. So we can write this differential equation as y quadruple prime, right? So fourth derivative of y is just going to be W0 divided by EI. All these are just constants. And in fact, maybe let's just relabel this rather than deal with all of these constants together. Why don't we just call it, well, I don't want to call it C because those are our, well, yeah, those are our constants of integration maybe. So how about K, as long as you don't get too confused. There's no springs here, so this is not the spring constant. So basically we just want where the fourth derivative is equal to some constant K. Oh yes, by the way, there's no time here. This is, you're not changing anything in time. Okay, so this is basically just a snapshot. So here we want y as a function of x, right? X being the horizontal distance. Again, we're calling this x equals 0. This would be x equals L. And then this being the x-axis, the deflection will be y as a function of x. Okay, so there's no t here, right? Okay, good. So you simply have to integrate this 4 times, and I think that's pretty easy to do. Should we do it one by one? Okay, so what would the third derivative be? Well, when you integrate k, you just get k times x plus some constant. I'll call that constant C3 or C4. I think I'm going to need 4 here. Yep. Let's call this C4 here. Right? So that's the third derivative. The second derivative, well, when you integrate again, you get 1/2 kx squared plus C4 times x plus another constant. We'll call that one C3. For the first derivative, you're going to get, let's see, 1/2 of 1/2 is 1/4, so you're going to get 1/4, k times x cubed, kx cubed, plus 1/2 c4 x squared plus c3x plus another constant, say c2. Maybe I had one too many constants here. So y itself, and that'll be the solution, will be 1/12 k times x to the 4th plus, let's see, 1/4 c4 x cubed plus 1/2 c3 x squared plus c2 times x plus c1. Okay, I guess it worked out. Okay. Now, on the other hand, the 1/4 c to the fourth is just some other constant. 1/2 c3 is just a constant, right? So we can relabel this as just c4, where c4 is really just the previous 1/4 c4, right? However, we don't want to get rid of the 1/12 because that's part of this k here. So we do need the 1/12 here, but not for not for these constants here. Okay, so is that okay? Okay, so that means my y of x, will just be, let's say, c1. Yep, c1. Oops. Let's try that again. c1 plus c2 times x plus, well, we could write 1/2 c3, but it's just some constant, c3 times x cubed plus c4 times x. Oh, I went too many exponents here. Sorry, c3x squared plus c4 x cubed plus, and then 1/12 kx to the fourth. I suppose we could just relabel this as k, but I'll keep the 1/12 for now. All right, so this is our general solution. Well, I mean, look, since this is just a constant, you're just integrating essentially 1, 2, 3, 4 times. Of course, you could have solved the corresponding homogeneous equation where this is 0, and then the particular solution, of course, will just be yp, will just be k again. So either way, you get the same result, right? You get this. Okay, so this is the general solution, but now, of course, we need to find c1, c2, c3, and c4. We need to find these constants, and to do that, we have to use the boundary conditions, right? So what are the boundary conditions here? Well, remember, this beam is simply supported. And if you remember, simply supported means that y is 0 and the second derivative is 0. Scroll up here. Yep, that's part C here. For a hinged or simply supported, you get the original function and the second derivative are both 0. And this is going to be true at both 0 and x, because it's simply supported at both ends, at 0 and, sorry, not x, 0 and L. L being the length of the beam here, right? Okay, well, let's just plug in the numbers here, right? If we plug in 0 for x, we know this becomes 0, so we get c1 plus 0 plus 0 plus 0 plus 0 is 0. So right away we get c1 is 0. Before we plug in L, let's plug in 0, but into the second derivative. So what's the first derivative? Well, the first derivative is c2 plus 2c3x plus 3c4x squared plus 1/3 kx cubed, right? 4 over 12 is 1/3. So now we can plug in 0, and we just get c2 plus 0 plus 0 plus 0 equals 0. So both c1 and c2, oh, hang on, that's the first derivative. Never mind. We need the second derivative now, right? Second derivative is 0. All right, so the derivative of c2 is 0. This is going to be 2c3 plus 6c4x plus kx squared. Yep. And now we can plug in 0. So, it's not c2 that's 0. It's actually c3. 2 times c3 plus 0 equals 0. So that tells us that c3 is 0. Okay, well, now we need to look at what happens at L, right? What happens at L? So we're going to plug in L into the original function, in other words, into this here. And what do we get? We get C1 plus C2L, right, plus C3. Oh, C3 is 0. Wait, hang on. Before we do that, maybe we should, yep, get rid of this C1 and C3 term because they're both 0. Okay. Now let's go back and plug in L. I mean, we didn't have to do that. That'll come out later, but we might as well do that now, right? So this is C2 times L plus 0 plus C4 times L cubed plus, let's see, KL to the 4th over 12. And we know that that has to be equal to 0. Okay. Well, remember what we're looking for. We're looking for C2 and C4, right? L is a constant. L is just the length of the beam. So we can't get it from just this. However, we need the second derivative and then plug in L. Well, the second derivative is here. And remember, C3 is 0. So the second derivative applied to L, change x to L, we get, let's see, 6 C4 times L plus K times L squared. K times L squared. And that still equals 0, right? They're all equal to 0 here. That's L squared. Okay. So I think from this equation, we can find C4, right? So 6 times C4L is equal to negative KL squared. Just divide by 6L. That's a K. And that tells me that C4 has to be negative KL over 6, or negative 1/6 KL. Okay. So that just leaves one more, C2. So if I plug this C4 into the first equation for YL, and I'm going to have to do that down here because I am running out of space again. Okay, so C2, that's what we're looking for, times L. And then C4 is this right here. It's going to be negative KL over 6. That's not a C, that's a 6. Times L cubed plus KL to the 4th over 12 equals 0. So let's see what we get here. Hang on, there's a plus sign here. That's a plus. Yep, so C2L plus. And this is the C4 that we got from here. Okay, fair enough. All right, so C2 times L, and then minus KL to the 4th over 6 plus KL to the 4th over 12 equals 0. And so what do we get? We get that C2 times L, so this is going to be negative 2 over 12 plus 1 over 12 is negative 1 over 12. So when you add that to both sides, you just get KL to the 4th over 12. And so finally, C2 is just KL to the 4th over 12L. So one of the L's cancels, and you get L cubed, right? So, all right, let me write that up here. So C2 is just KL to the 3rd over 12. Okay, so that gives us all our C's. Now we can go back and write the actual solution here. So let me do that down here. So y of x is going to equal, again, C1 was 0. C2, what was C2? Where's C2? Yes, here, KL cubed over 12. So can I write that as 1/12 KL to the 3rd times x, right? Plus the C3 term is 0. And then C4, C4 is going to be negative. See, negative 1/6 KL, just KL, right? Yep. And then times x to the third, right? And then this term here stays the same. This is still 1/12 kx to the fourth. So I think that does it. Although, when you look at the answer in the book, remember I substituted k for this quantity here, W0 over EI. So maybe we should put that back. In fact, k is a constant. It's in every term. We can actually factor it out, right? So if you factor out the k, and remember what k was, W0 over EI. So we get W0 over EI. And while we're at it, why don't we factor out the 1 over 12? Right. So what's left over here is just, L cubed times x, cubed times x, minus, and then, right, so this is 2 over 12, so we need a 2L times x cubed, and then plus 1/12 k is this stuff here, so this is just x to the fourth. So that's, that's just another version, another way to write it, and that's probably the way the book would write it, given that the book didn't use this substitution here. So I just use this k for convenience. Again, there's no spring here. This is not the spring constant. I just didn't want to use c, or some other weird letter like t or w. Off the top of my head, k works here. So anyways, so that solves the equation. This you can check if you plug this back into the original equation here. That should solve it. So that's I guess that's the example I'm going to do in section 5.2. So this is a reasonably simple example for a boundary value problem.